That's fine. Yeah. Yes. Okay. Okay. Welcome back, everybody. So we will continue. Yeah. Thank you. All right. So we will skip a bit of this. Few examples. Maybe I'll come back to this fraction example if there's some time. Yeah, because something interesting. Let me. Okay. Yeah. So we are here. So I will talk about two examples of teaching to give you a flavor for how sort of research about teaching, understanding teaching goes on. What kind of things one notices and things to be important. So one is this teaching long division. Also some comments about how actually one can change teaching over scale, changes in the curriculum, etc. Maybe relevant to some of the work that we were trying to do. Okay, so this you're all familiar with. I think you understand what I mean by long division. It's that algorithm in which you do division. We learn typically. I think this is from the class 4 textbook, so it's around that time that kids learn this. This is the class 4 textbook of the previous reform, right? What's called NCF 2005. I don't know if this is a familiar phrase, National Curriculum Framework 2005, which was a big change in education soon after the government changed in 2004. It was a major curricular reform of school level, led by very able educationists, of whom Krishna Kumar was the main person, was the chair of the whole process, and involved, about 200 people, very good experts from all over the country. I was part of it, and it was a lovely experience. So new textbooks came out, and especially at the primary level, those textbooks were pretty attractive. And I'm going to pick up one example from that textbook, which was a change. I'm not showing you what was it there before, but you can guess. Division was introduced by saying dividend, divisor, quotient, remainder, explaining those things, etc. Now, in the new textbooks, this was the way division was introduced. It's sometimes described as the partial quotient method. So you first, instead of dividing 9,588, you kind of divide part by part, and then you go on accumulating the quotient. So it's a okay. So now I'm going to show you another video. Hopefully, this will work for the people online. Apparently, we can't hear the sound. But my apologies if it doesn't work. So. Okay, so this is the problem which was put before this. So now this is a bit of kind of teaching video. Sound and all that may not be clear, so I'll pause in between. If you have any questions, you ask me. 4 friends put up a juice stall for the school fair. They made a profit of 96 rupees. If they share it equally, how much should each one get? Okay, so what's happening there is that there is a boy called Aman. You can see on the board that he has done something. He's written 224 times and he's added it up. And in the classroom, there was a general culture that he can be asked some questions. So the other children are shouting question, head question. And they are going to ask him a question. So the question is, how did you get 220? That is the question. And here, Aman is trying to explain how he got 220. Huh? Okay, he struggled a bit to explain that how it is 224. Not very successful. So after some time, another kid comes. It's a bit faint on the right side. He does the actual standard long division algorithm on the right side. And so that's there on the board. And now the teacher does that. Okay, so you all noticed and reacted to some things happening in the video. So it's quite nice. I mean, I'll talk about that particular example first, maybe, and then come back to discussing other aspects. So why does it work so? I mean, it does work right. This what is called the partial quotient method. And here's another story of associated with this particular thing. Now, this Pallavi is a primary teacher with 25 years of experience. So she is very, very experienced. And this is reported like a case study. Again, it's from Tucker's work. So what she said is that she was teaching the new class 4 textbook, in which the picture I showed in the beginning was given. And she was very unhappy. She said, look, you can't expect them, the students, to learn so many methods like the new textbook gives. It says you teach this method also, that method also. It's very confusing for students. Then when you ask a question, which method do you want them to use? They should use long division. It's what we have been doing for ages. I did it when in school, and it's the systematic way. Right? So this is what she said, and she was quite unhappy with this. And there's a thing highlighted, that you have to teach the method.
Right, so this new curriculum you teach both long division and this partial.
That's what she said. She said that look, you have to teach all these methods. Better go straight to the proper standard systematic way of doing it. Why do all these halfway things? So then the researcher, so there must be a reason for why an algorithm works. And don't you think it's important for students to know why this method works? So the teacher says, look, they're very young. When they grow up, they go to class 7 or 8, you can tell them, see, this is why we did that, but not now. They're too young, they just get more and more confused. The brains are too small. I think she even said something. But this is the typical, you recognize this, right? And this is what we tend to think. So, because Shika was going and sitting in our lessons, so she told Shika that, okay, you do one thing, you teach this in the class. So the teacher invited the researcher to teach this particular topic for class 4 students. Now, it was a very interesting class because Shika did it for about, I think, 10 minutes or so. She gave a problem, and exactly the same way, some grandfather wanted to distribute some money to his grandchildren, and how much did each one get? And the kids came up with different things, which she all recorded. Each way of doing it, like that partial quotient thing. And then the class was very engaging and excited. Not only that, Pallavi teacher got very excited. She stood up at some point and told Shika to sit and she took over the class. She did this. So this is what is described in the paper, and Shika talks about, I'm also a co-author. She talks about what is it that made her change her mind in some way. And she did change her mind because she said after the class, because this was a discussion they used to have, I think the method is good. The students can use different ways to get it. Also, it's very clear, this vertical arrangement of numbers. Actually, the number of steps increases if you take small numbers at each step. But it doesn't matter because they anyway get it. This method is better, and they picked it up faster also. They find it more easy only enough. So they can make as many groups and how much ever they want. So this is, it's very flexible. And then she goes on. But one more difference is there. In long division, I have to teach them for each increasing digit, like dividing by 1-digit divisor, 2-digit number, 3-digit number, etc. They're all different. But in this, they have to use the same method for big numbers by themselves, and they can do it. So this is what. So she felt, enthused about this particular thing because she saw the students responding and picking it up, and that's what is described in that paper. Now this is the same thing. Why am I showing this? I tell you. It's wrong or something.
It's 18 is the.
It's from a paper. It's from a published article, and which shows the students doing this kind of. In fact, that's the paper in which I think I at least first came across this term partial quotient method. And this is by Shreya Kemani and Jayashree Subramaniam from Eklavya. At that time, both were in Eklavya. And they wrote this paper for the conference, tackling the division algorithm. And they found that this partial quotient method really works and gets picked up by teachers. Not only that, this is from another paper. This is described by this is part of something called the school mathematics project. It's the same thing. It's the same partial quotient algorithm. And it's the school mathematics project was a project done in Delhi, led by Delhi University Physics Department, Amitabh Mukherjee, if you know him, Vijay Verma. They are the authors of that project. And there they worked with teachers who kind of develop lessons and curriculum material and go and teach in the schools. And so they tried many things. In fact, I think there's a quote. So in the course of the intervention period, 1995 to 2000, a host of alternate pedagogical strategies were developed by the program teachers through a dialectical process of classroom trial and discussion and group. The teaching of long division is taken here as an example. This is from the paper. Teachers reported that in spite of the contextual exercises, children found it no easier to follow the algorithm than with the conventional approach followed earlier. At group meetings, several suggestions were made to modify the algorithm so that it was made somewhat more transparent. Some were tried out and rejected on the basis of classroom trials. Finally, teachers reported that the way of doing long division given below worked the best. So that's the partial quotient. So, of course, the school mathematics project was one of the inputs into what was at that time in the early 2000s, division of the Delhi school textbooks by the Delhi government, and which was some of the same people were also involved in the HCF textbook revision, so that found its way into it. So, the first point is that, when the reason why that algorithms works well, and teachers, once the teacher initially rejected it, Pallavi teacher, but when she saw its power, she did get sort of views changed, and that's because it requires a certain number of trial before it's introduced in different contexts, and that's very important. Different projects. One in Delhi, Eklavya in and around Bhopal. We also tried something like that in Homi Baba Center, plus other places. So it's tried out in multiple contexts, found to work, and then it becomes something stable. Also, and it's not that. So there is a prior work that's needed, which comes, I think, in the next slide. So researchers working with teachers is powerful to create conditions for research. 3 different cases of researcher positioning. One is teacher-researcher groups. The other is Kemani and Subramaniam, who actually directly taught in schools. But like the way I was also teaching kids. Collaborative professional development, which Shikha was working with teachers. So, yeah, it's the second bullet that so curricular change, if it's got to be stable and if it's got to be something which works, it's got to be, in some sense, institutional. Teachers are a very big part and they should come on board. And it can't happen so simply. I mean, if you sit around the table and discuss ideas and change something, it may or may not work. So you need something that which I've described as prior didactic work, using this particular example, but I will take another example of that as well. That you need this sort of trialing in different contexts for something to really become stable and valid in some way for introducing into the curriculum. And that's unfortunately there are not many opportunities for it. Yeah.
So I'm a little surprised that the last bullet point is sort of pointed out as what we learn from this example. I'm a little curious why this last point should be self-evident. That because after all, new models of how to learn, they have to work in the classroom, and they have to have a degree of teacher buy-in. So it's rather surprising to me that that one point is portrayed as something that one as a eureka moment, because I felt that should underpin any kind of framework, isn't it?
Yeah, yeah. So the reason why unfortunately becomes something that is not immediately obvious is because we don't have institutional spaces where this can happen. Where would it happen? Would it happen in B.Ed colleges? Would it happen in the NCRT like or SCRT institutions? Would it happen in universities? So that's partly the reason why it's being highlighted, that it can happen in small NGOs, for instance in Eklavya, or small governmental organizations like the Homi Bhabha Center. The school mathematics project was something started by the physics, some committed teachers in the physics department of Delhi University by setting up a separate center which ran for a few years with some funding and then folded. So we don't have institutional spaces, and part of the larger argument which I have been making in some other writings and fora is that to look at our system and see where these institutional spaces where such trials can systematically happen over long term can come up. And I suggested that this has to happen where in primarily institutions of learning which are higher education institutions like universities, or in fact I took ISERs as an example. Because in the teacher education space, the B.Ed, those are called teacher education institutions, they've divorced subject matter from pedagogy. They become two different things. So this is, real change requires bringing together a board, and you require inputs all, from the subject perspective. So inputs from mathematicians, from scientists, in the case of science education, is very important. And for school education, unfortunately, higher education institutions in India don't deal with school education. They're left to other completely different institutional spaces. So that's really the background for why I'm saying this. Of course, when I started work in the Homi Bhabha Center, we were developing curriculum. It was very obvious that we had to go and teach. And at least my seniors were doing that. And it was, so we went to schools and we taught before we put something into a textbook, and my colleagues did the same. But that's not, so Homi Bhabha Center is like one tiny space. Doing too many different things.
So
and, yeah.
Did I also understand therefore that the awareness that prior didactical work is needed does exist, but as you said, there are just a few isolated spaces where this can happen. So you call it as something we learn so that the policymakers who I may not expect to be aware of this take note. Is that
they would be aware of this. They would be aware of it, but they're not empowered enough to change things. Who's empowered to change things? I think it's those institutions which can potentially take up this, like the ISERs, maybe even IIC. So it's part of a broader argument for starting centers or departments for STEM education at the school level in institutions of higher learning and research. Anyway, this we can skip. I mean, this is, so typically one would apply these kind of criteria if you're sitting in a committee and developing textbooks or curriculum material. You check for all these. Is it age appropriate? The cognitive level, is it appropriate? Is the content scientifically correct, mathematically correct, accurate? Process validity, the way in which the pedagogy is transacted, is that taken into account? Some amount of historical validity, knowing that it's evolved. Don't thrust concepts too quickly if they are complicated histories. Environmental value, it should relate in some way to the child's environment. And of course, ethical values should be consistent with value. So these things one can kind of decide around in a committee around KP, one can check. But the fact of this prior directly go is not easy. It requires time and commitment to some kind of an ongoing act. And that's the spaces that we lack. The other thing is to understand, I mean, which is very powerful in this example, is that meaningful learning. I mean, you see that children, they pick up things when it makes sense to them. In fact, what the partial division algorithm does is it just translates. It's a way of recording what the child did intuitively. And it becomes a kind of halfway, it becomes a bridge to the standard algorithm, which is also needed. It's also important to understand why it's needed. It's needed because you use it to continue division beyond the whole numbers, into decimal numbers. And that's the way to do it. So you need that standard algorithm. Yeah, and so meanings are important. And unfortunately, this is again something not all educationists are convinced of. Particularly things like mathematics education. They feel that, okay, understanding can come later, let them just get it right. You know, this sort of thing. It doesn't work with a large number of students. It works with some students. It works very well with a small group of students, you know, which is probably all of us in this room, that, but the majority of students doesn't. Okay. The other thing, maybe I should have had one or two more slides on this, which is that some other things are very interesting, which I became aware of only when I started doing work in education. The discourse in education throws up those kind of constructs or concepts. That you all reacted to Aman, that kid, and it's a very delightful thing. One thing he was very good at was addition. For some reason, he loved addition. You solve every problem doing addition. You know, later on when I looked at his written work, I saw like pages and pages of just adding numbers. So at one point, you know, he grabs the chalk from, right? So this is, it's an important moment because it is taking ownership of a particular device or a particular representation. So it becomes the child's. It's no longer something external. He says, okay. And something similar happens also with Pallavi teacher. You see, she takes ownership of that approach to teach. So these kind of constructs are also important. Constructs which are fundamentally, in some sense, to identity is another important construct. So, you know, many kids don't take to mathematics because they feel it's got nothing to do with it. It's something that other people do. It's not something that concerns me. So there's no engagement with mathematics because you don't identify with it at all. So often the challenge of teaching is to find something that is connected with the student's identity and also connected to the content that you teach, or to modify the content. As a teacher, you realize that, okay, this is what is important, interesting, engaging for my students. So let me go that way. You know, so maybe they'll gain something. So those are all important learnings from that particular video. Okay, I have another example. This is the last one. So would you like to see that? This is also teaching fractions. This is another topic in which there's been enough prior directly working. And it's, I think it really works, and fractions are very hard, very difficult to learn, and people have also analyzed the reasons why it's difficult to teach. You know, the notation invites interference from whole number knowledge. So you give two fractions and ask them to compare, they look for the ones which are bigger numbers, like 10 over 15 and say 3 over 4 or something, and then they say that one is bigger. Addition, subtraction, adding numerators and denominators. Actually, that was there in the earlier example. That's one. The other thing is that the fraction notation is connected to the division operation, which is inherently more difficult. It's the last thing that of the 4 operations they learn. So it's more difficult to grasp. Understanding fractions requires a major conceptual change, which I'll talk about a little later. Fractions are not really used in the real world. They used to be used a little more earlier, but now we just use either percentages or decimal fractions. We don't use anything else. So there's no support really from the real world. There is some cultural and language support because it's come down from earlier times. Particularly Indian languages have words for quarter, even half quarter in Marathi is common. Tamil old words exist for pretty tiny fractions, all that. So they are not really tapped. And the world of work, like Arindam Bose's work, which I mentioned at the beginning, you do find many examples of fractions in, say, the old British system, or historically even currency was, not decimal currency, something else, and so on. So these kind of resources are not really tapped in learning fractions. And the application of fractions in real life, for instance, one application is as ratio. We use fractions as ratios, combining ratios. The earlier example, I didn't mention it, was a challenge for the teachers, because one common error that students do is to add numerators and denominators, right, when they add fractions. So the teachers have said that, okay, when you calculate the students' score marks in geography and history and put down a total for social studies, then what do? So you add, if it's 40 out of 50 in history and 30 out of 50 in geography, you will add the numerator and the denominators and you will score. So why do you ask the students not to do this? This is it. And then there's some discussion. So the reason, of course, is that there we are treating fractions as ratios. They're not really measures. They're measures of the kind of quality of performance. And then you're trying to do some kind of weighted average of two performances which you want to take together. So that's very different from saying that using the fraction to say how much of there is of a certain point. 2.5, 3.5 feet, etc. So that the meaning of fraction, interpretation and context can be very, very different. So, and this is some important work which has been done, which talks about, which argues, this is a bunch of psychologists actually, more than, but some math education people have also agree with this. So they say that there's a major conceptual change from whole number to fractions, and not all children make this shift, transition. And the children who seem to succeed many years down the line in mathematics are children who actually manage to make this shift fairly early. What are the shifts? Whole numbers, there's a next number. Like given a number, there's one successor, there's one predecessor. And there's no number between two consecutive numbers. But in fractions, there's no next number in terms of ordering of size. And between any two fractions, there's an infinite number of fractions. You can go on finding more and more fractions. Whole numbers, there's the smallest non-zero number, which we take as the unit. In fractions, there's no smallest non-zero fraction. By the way, fraction means a positive fraction, other than whole numbers, symbols are a shorthand encoding of multiplication. So tens, units, tens, hundreds, thousands, etc. Involve addition and multiplication. But the fraction notation is actually based on, it encodes a division. It's a quotient. notation. Whole numbers, comparison, addition, and subtraction are supported by counting. So you begin doing addition, subtraction by using counting. So you have a very secure basis for doing addition, subtraction, not that for fractions. You have to learn something totally different. So this is a group of Greek subjects, cognitive psychologists actually. Okay. So given all this background, there are two key meanings of which support fraction learning, and I think that's been tried in different contexts, and it's something which works. So one is that the notion of fraction, the meaning of fraction as a measure, that it tells you how much there is of, say, length or weight, volume, etc. And it's between whole numbers. So it's like, say, more than 2 kg but less than 3 kg. So what's that? And you can say more than 2 meters, less than 3 meters, etc. And you do that by taking the basic unit, which may be a meter or a kg, as the case may be, and you make smaller units, what are called fractional units. And you do that by dividing it into n equal parts, and you get a fraction. So the way to understand a fraction is m by n is m times 1 by n. It's also encoded in the word phrase like 3/4, 5/10, etc. Now, unfortunately, this is different from this what's called a part whole. You take a picture and you shade some parts out of a total number of parts. And it's a kind of ratio idea, and it's not very helpful. In fact, it interferes. It tends to promote thinking of fractions as 2 whole numbers. One account of those parts which are shaded, the other which is the total number of parts, and they don't really shift from whole number thinking, but this makes it more explicit, that you're actually counting the number of fractional units. And the denominator is so-called because it denominator means it names like a denomination of a currency. It tells you its value, what the value is of the unit. While the numerator is the one which enumerates or counts how many of the units. So that's also the meaning of it. So that's a very fundamental meaning. And the second meaning of fraction is an equal share. And so both these mean that when you have m units are divided to n portions or n equal shares, each share, the magnitude of each share is m by n. This is the other idea, and that's called the share unit. So both of these have to go hand in hand, and it's quite. I mean, many kids do grasp this. So let me see. Okay, so there's a fraction video that I will show. So this is from, these were nice videos made by Eklavya, the organization in Bhopal, Hoshanabad, Madhya Pradesh, many years ago. And it's there on YouTube, actually. So if you do Eklavya fraction teaching or something, I think it's called. So if you do a search, because it may 16 by 3 not be very clear. It's, I think, 16 by 3. That's right. So she's trying to divide 16 rotis or whatever into 3 sheets. he is the teacher, excellent teacher, very good understanding of, I think it's maybe now with Azim Premji University. Okay. The many interesting episodes. I think the video is maybe for a total of some 30-40 minutes, I think, in all, in different parts. And you will see how the kids. So although Sunil Verma, the teacher, mentions only the share model, you can see that they're also working with what I would call the measure model, which is the accumulation of fraction units. You know, to see that this is 1 whole, this is 3 by 4, and then even the pieces that you saw. So they also part of, they show the fraction units. It's a very nice kit developed by Jodogyan. In fact, Jodogyan is one of the agencies which has really tried the fraction sequence at primary school, you know, class 5, 6, very well, and it's really worked. I think it makes a big difference because kids, otherwise most kids will say 1 by 5 is smaller than 1 by 6. You know, very common for class 5 kids to say that because they just go by the numbers and the symbols. Not so the quantity aspect comes to the fore with those approaches. Let's see. I think it's more or less. Yeah, that's it. There's some fun thing which I just wanted to show at the end. No, this time. Yes. Okay. So then I need to show that the example I was telling. Okay, this is the example I was telling you that, which is a challenge we put to teachers. So, what you notice here, I have time to read it, I think, is that there's a very nice mathematical theorem here, right? If A by B and C by D are two fractions, and say C by D is bigger than A by D, then if you add the numerators and denominators, you get something. It's quite nice. Why is this important? I mean, this is almost never done in curriculum in school. It's important because it's, you see, children need to understand the property of density, right? That between any two fractions there is a fraction, and that's what makes it completely different from whole numbers. And so you can find fractions between two given fractions in different ways. And one of the nice ways is this, that you can find it simply by adding the numerator and denominator. And it's also led to something connected with something that, in fact, occurred to me much later, which is that when you interpret fractions as equal shares, it becomes easy to compare. Like, why is 1 by 5 bigger than 1 by 6? When you have a roti shared among 5 people, each one's going to get a bigger share than if it's shared among 6 people. So this way of thinking actually facilitates comparison quite a bit, and you can go quite far with this. So that's a picture of 2 by 3. So we'll show it this way with some stick figures and say rotis. And then, okay, that's supposed to be some. Now this is the comparing shares. Of course, the example I gave is easy because the numerator is the same. So rotis are the same, children are different, easy to compare. Similarly, if children are the same, rotis are different, easy to compare. If rotis are less, children are more compared to the other situation, again it's easy to compare because it's, just goes on. The difficult case in both of rotis are also more, children are also. Then you have to, that's the difficult case to compare. So kids learn this. So this is the tricky one. And here is a very nice argument for comparing, say, 2 by 3 and 3 by 4 or 3 by 5. What you do is you split the 3 by 4 into two groups, 2 by 3 and 1 by 1. See, the first subgroup gets the same as the first group. The remaining kid gets a little more. So which means to equalize, he has to share what he has got with the others, and everyone ends up getting more. So 3 by 4 is more than 2 by 3. And the same thing works here, which is that subgroup gets the same. The second subgroup is going to get less. So you have to, why is it less? Because you can see that half, there's more than 1.5. So each one's getting more than half, etc. So you can see that therefore 3 by 5 is less than 2 by 5. So this is a nice kind of discussion, and there's some kind of a theorem here, which is that when two subgroups hold different equal shares, equalization will mean taking something from the greater and giving it to the smaller, something like that. Okay. So this gives you a way of actually comparing. It's a sort of descent algorithm. You take A by B and C by D, and that's the social science example. The theorem says that if you go to compare A by B and M by N, where M is more than A and N is more than B, then you rewrite M and N as A plus C and B plus D. And then you need to only compare M by N with, A by B with C by D. And then you can recursively do this, and you get to compare smaller and smaller fractions. So it's a kind of some fun thing to discover about. And all of these explorations about, I think, fractions are important because to get a sense of what they are in terms of magnitude. So that's it. That's my last slide.
You always say that learning procedure first and then bothering to understand is a bad idea. Was that your point? Or are there some situations where that works better?
So I think it's also a perspective about what's important in mathematics. I think the need for learning procedures becomes less and less, and the need for, I mean, at least in terms of practical application. There is the internal need, like if you know, you have to know multiplication tables. If you want to learn, say, middle school mathematics or high school mathematics, it's going to be very difficult to learn if you don't know, say, if you can't do multiplications fast. So there are certain things you need to internalize. The problem is that these procedures, if there's something at one time very popular called bug theory. That is there's an algorithm, and some piece of the algorithm is missing from memory. It's gone, like addition. So you do something called a repair. You fix it. Now, which may lead to wrong answers. So lots of wrong answers are being analyzed this way. The problem is that you don't have a reasoned basis for covering the gaps in your memory. What you fail to recall, you can't have a reasoned basis either by reasoning it out or by checking, validating in some other way. So it's important to learn things with reasoning and to develop that reasoned basis so that you can fall back on it when you forget something and not do some surface repair. That's one way of looking at it. The other thing is, I think, in the long term, it's the reasoning which pays off. And
no, I'm assuming that in the end you know both procedure and reasoning.
The sequence of what you.
Yeah. For example, learning square root calculation, we always learn no idea why that works or something.
Yeah.
What's later?
It's very hard to figure out. So anyway, we dropped that. And that's an example of something that
it's not necessary.
Not necessary. So many things are not necessary. And you can do some alternative algorithms for finding approximations for square root, etc. Trial and checking kind of thing. Yeah, so I think in most cases it will not be that important. Maybe there are a few where it's important. I can't think of any. That's
for example, calculus, the way it is
yeah.
It's good. It's not good enough for a math undergrad. Honors, not honors.
Actually, calculus is a good example. And that I don't have a judgment on that. Because I think, say, if you look at engineering, physics, I think at least the way the curriculum is structured now, you just need to know techniques of differentiation, integration. Otherwise, you can't get by. And so there, I don't have an opinion on what really matters.
No, anyway, you are talking more at for primary education.
But even there, I think lots of good teachers try to build intuitive feel and understanding. It's challenging, particularly for calculus.
Example of parliament, the intervention by the researcher, she gave an example and took the class for 10 minutes. There's something special that happened during the 10 minutes. It's created.
She followed this partial quotient thing, which was in the textbook, which Pallavi
So the
teacher
teacher
was
was not trying to
no, she's very reluctant to teach it, right?
teach it.
Maybe she tried it and gave up his mind. What is
So I think an example of someone doing it and seeing how the students are responding to that.
It works. It can be quite powerful. And like the video I've shown to many teachers. So it does trigger something. But nothing like seeing it happen in your own class. I think that's something special.
Like you said, how Aman got ownership of it. Once he understood it, the teacher also got ownership once he understood it.
Yeah. That's important.
One issue I have with that experiment is that if somebody from outside, an external teacher is coming and teaching, students will naturally be more paying more attention.
Yeah.
Necessarily tell you
That's true. I mean, it's good fun to have somebody come and talk to you on this. That's true. But in this example, I think the more important thing was Pallavi teacher took back the class and continued that. Yes. And she did also get a good response.
So that sometimes when you're teaching some complicated algorithm to kids, they might try to pattern match rather than actually learn the algorithm. They look at numbers and associate, okay, I see a 6, so number division maybe there's 3 or 2 operating in how are you avoid that?
Yeah. This is, I mean,
I remember I fell into this trap as well. For a long time, I did not properly learn control long division. I would just guess the numbers.
that's the numbers. Yeah, many kids do this. In fact, there's a classic math education research paper about a student called Benny. I think you Google search Benny's BENNY. Benny's mathematics. We do it in all our courses. So this was in the 70s when there was something became fashionable called programmed instruction. I don't know if you all. It was an earlier version of this software-based learning. So you divide the math concept into tiny steps, and you have one worksheet in which the answers are hidden, and then you use a mask and then answers show up. When I was an undergrad student, I found such material in the library. That's a typical behaviorist paradigm, and it's supposed to be self-learning material. Nowadays, you also have these self-learning online materials, which give you feedback about whether something is correct or not, but they don't really focus on teaching the concept or the understanding. And then Benny tries to guess he does this pattern matching. And it's fascinating because his answers are absurd, except sometimes they are right. And the way he argues for them it's a fascinating, there's a huge influence. Very influential.
Okay, maybe it's a good time to stop. Let's thank the here.